Hi, I get lots of email technical questions. In this particular case, I got one from somebody who wanted to know how to design like really low standby power direct mains power supplies, i.e., 240 volt or 110 volt mains rectified and powering a product directly, non-isolated, as we'll go into. But they wanted to have like really low standby power. So usually technical questions like these take a long time to answer, so usually I direct people over to the EEVblog forum to answer such things. But I thought, hey, this might make an interesting video, so I thought I'd actually get a mains powered product like this. In this particular case, it's one of these photoelectric smoke alarms. It's a 240 volt one that actually powers into the mains. It's actually dual battery and mains powered, because if the mains fails, you need the battery backup for safety, of course. Model Q 1300. It's a Quell, which is a big brand here in Australia. So I thought we'd do a teardown of this and have a look at the design and look at how much standby current something like this uses, and potentially how to actually design, or one of the ways to actually design a really low standby quiescent current direct mains power supply. So let's take a look at it. Now, just a quick note on the product design of this thing. I really quite like this. It's got the backing plate here, and of course you screw this into the ceiling, and then it's got a hinged system like this, and it's got some screw-in terminals for the mains. Of course, you've got to have that, so your 240 volts goes directly, and they look like proper cage clamps too. None of that spring leaf lever rubbish. I really like those. So that's really nice. They've got an extra cover which then goes over that to isolate, but when it goes down, here are the pins on the PCB inside, so when it goes in like this, it goes down and then slides across like that and makes contact in there, as well as retaining it on the roof. So yeah, hats off to the designers there. That's very nice. And we've got our 9 volt battery backup in there as well. And no, it's not rechargeable. It just uses a regular 9 volt PP3 alkaline or lithium or whatever you whack in there, and that just it's probably got diode, or we'll reverse engineer the circuit in here and have a squeeze. But anyway, rather like the design of that. And also the design of this little latch here, when you put the battery in there, it pushes down and moves that lever out, and that means that you can't actually close this up and then slide this in and install it without the battery physically being installed. That's a really nice design touch. I love it. Yeah, this is a photoelectric one, as I said, photoelectric sensor. So what that means is that it just, like the smoke particles go into the sensor here, and then it uses optical measuring to see if there's any particles within the air inside the sensor. So it doesn't have any of that nuclear rubbish. And right off the bat here, the spec, it's only got a maximum spec, but look at this, 80 milliamps, 240 volts AC. Whoa, geez, that's a fair bit of current draw. But yeah, it won't be that max, we'll have to measure it. And there you go. Wow, that is truly horrendous. 563 milliwatts. Wow, that's awful. And look at the power factor. 0.062 power factor, so that gives it a VA of over 9 VA. Gotta be kidding me. This is like, obviously they're using an just a bridge rectifier in there, Zener Diode type configuration or something like that. Absolutely no thought given whatsoever to actually minimizing the quiescent current of this thing. And well, what's the big deal, Dave? It's only half a watt. What's the big deal? Well, I've done videos, which I'll link in, on why that can be a big deal. And sure, you're only in like residential situations. Generally, it might vary in some countries, but you're only going to pay for the half a watt here. You're not going to pay for the 9 VA here, but that is current that has to come from the grid. So even though you're not paying for it, the grid infrastructure has to be there to enable this. So we're looking at 36.5 milliamps at 247 volts. Yes, I am right on the high side of the mains voltage, which is nominally 230 volts here in Australia. So to give us our 9 VA, so that's just, yeah, that's nuts. Let's run some numbers, shall we? So that power consumption is absolutely atrocious. We'll go through the numbers in a minute, but I thought that, well, maybe it's just this Quell design. So I went out and bought this sort of like no-name Fire Pro, I guess. Well, let's check this out. It's not promising though. Look, 100 milliamps max. The other one was only like 80 milliamps or something. So, measure this one, but I reckon it's going to be a shocker too. Built down to a price. The design of this one is nowhere near as polished as that Quell one. Anyway, let's power it up. Wow, this is an absolute shocker. 1.36 watts. Are you kidding me? That's enormous. Once again, same power factor as we're getting before. So our VA is getting 19.5 VA. Are you kidding me? People have like half a dozen of these things installed in their house. This is shocking. I'm going to call it. This seems to be a systemic design problem with these like 240 volt home smoke alarms. Let's run the numbers on this. This is insane. So let's run some numbers here. Let's say we had this Fire Pro brand installed all over Australia. Oh, don't touch the dangerous part here. Yeah. Anyway, let's say we had these. Let's say, you know, a typical large home might have like 5 of these installed. You've got to have them installed in front of every or inside every bedroom and stuff like that. There's new requirements these days, things like that. Let's say we have 1 million homes in Australia. I think there's like 2.5 million, but just, you know, let's just round. Let's say we've got 1 million homes installed with 5 of these each, right? We're talking, let's just round this up to 20 VA, okay? And because even though the residential customer is only paying for the watts, okay, 1.3 watts, the grid has to be designed to deliver this entire 78 milliamps, right? You don't get that for free. That's losses in the grid, even though you're not paying for it. So the generator has to produce that. The transmission capability has to be in there for that. So let's just call that 20 VA, right? So this is apparent power or complex power as opposed to real power or active power as it's called. But as I said, you've got to generate this at the generation station. It just goes to show how bad product design like this, or really essentially cheap product design, because we'll have a look at better product design in a minute that's more expensive that can solve this problem. This can have a real huge environmental and cost impact on the planet when you start talking millions and tens of millions and hundreds of millions of homes that all have these smoke alarms mandated. You don't think, oh, the smoke alarm's taking NAF power, and it does when you power them from your little 9-volt battery here, because normally these things will last a couple of years off a 9-volt battery. So the actual electronics in here detecting the smoke takes NAF power. It really does. So all of that, like 99.9% of it, is being wasted in the mains rectifier in here and the power supply that needs to power that circuitry. It's insane. And well, to the surprise of absolutely none of my audience whatsoever, yeah, this is the cheap Fire Pro one, and this is the more expensive one. It's actually designed by Kitty. I've heard of them before, so yeah, Quell don't design their own. But, yep, these things are built down to a price, as you'd expect, and we're paying the price in terms of environmental cost, because these mains power sensors use, like, in the order of 65,000 times more power than the equivalent just being powered from the battery. The same thing. It's just insane. Absolutely insane. And we've got our piezo transducer as well, and this is actually the sensor. And you can see where the smoke's actually going to get into this one. If we have a look at this Kitty / Quell one over here, you can see that this is where the smoke goes in around here. I was actually wrong that the smoke goes in through here. This is actually the buzzer. It goes around the outside and then goes inside the unit and then makes its way through the grill here into our photo sensor here and here. It's interesting to note that this cheaper one actually uses a tactile switch here for the test button, but the more expensive one over here, well, I presume it's more expensive, actually just uses a PCB contact and just some bent metal like that making contact to a link over there. So I do wonder which one's actually cheaper, because, you know, you can get these for cents at the Shenzhen market. I wonder how much this solution here cost. It's interesting. Anyway, this one, is this a double-sided? This one looks like a double-sided FR4 board. This one over here, single-sided jobby, because you save a few cents on that. Anyway, both of them have a MOV, because you don't want any surges, of course, on the power line, because these things are hooked up 24/7. So both of them have a little MOV. That one's got a little slot cut out underneath for isolation, but basically it's a capacitor divider and a big resistor. Capacitor, of course, at 50 hertz, none of that 60 hertz American rubbish, 50 hertz Australian mains, and of course a capacitance will have a given impedance, and then that works in combination with a resistor here to give you a resistor divider. And it looks like, is that our Zener up there? Could be. So this one here uses a 1 mic. Both of these are X2 class capacitors. Of course, proper mains rated self-healing types with all the requisite approvals on them. So this is the Kitty/Quell. This is the Fire Pro here. You got a smoke alarm controller IC here. It's a custom ASIC. We've got bridge rectifier down here. I can't see a bridge rectifier over on here. It might be just a half-wave jobby. Not sure if you can see that, but the more expensive one, there you go, got the shine on it. It looks like it has at least partial conformal coating on it, just to stop moisture causing a problem. So I've reverse engineered the mains input power supply on both of these, and as suspected, they're just a simple Zener Diode based rectifier. That's it. So we've got our 240 volts in here, line and neutral. We've got a series resistor here. That's a big 2-watt jobby in both places. Then we've got that X2 240 volt rated mains capacitor. We've got a MOV here doing some protection after the resistor, so that's good. We've got some bleeder resistors across here, just some high value ones. One of them had 3 resistors in series just to get the voltage, because they're SMD ones, so they're only rated like a couple hundred volts each, tops. So they put them in series to get the voltage rating. Then we've got a Zener diode. In the case of this one, it actually used, this one over here used 2 Zener diodes here and here in series. This one over here only uses 1 Zener diode, but works exactly the same. Then we've just got a regular Joe Bloggs diode here, and then an electrolytic cap, and then that buggers off to the ground in here. Now, of course, these are what's called a direct mains connection, non-isolated power supply, and these are inherently dangerous. You do not design these except in products that are fully enclosed like this, where the user can never ever touch the electronics in them, or shouldn't. That's the entire point, because it's more cost and complexity to put in like a mains isolation transformer and everything else. But in these types of products, it's no problem, and it's completely legal to have your circuitry over here mains referenced over here, even though it's the neutral. And technically we use the MEN system, the multiple earth neutral, at least we do here in Australia. Your mileage may vary, and the neutral is connected back to the earth at your switch box, but you can't assume that the wiring in a house is correct, and some idiot may have swapped active and neutral here, and you could completely come a gutser if you designed a product that was relying on the fact that any exposed user accessible ground or metal or connector or anything like that was reliant upon directly connected through the neutral. You're going to come a gutser, and that's inherently unsafe. So you don't want that. So a non-isolated power supply like this, they're very common to find in these type of sealed enclosures like this, because you just don't need the isolation. But this is where the poor power factor comes from. It's just using the cap and the series resistor as a dropper effectively for the Zener diode, and that's just, no, that's what's resulting in the piss poor power factor that we're seeing. So there's just no way of avoiding losses in your traditional Zener-based circuit like this. In this particular case, I'm going to measure the voltage directly across the 100 ohm resistor here. Got it there, and 7.9 volts. So there you go, that's 79 milliamps, and of course that's going to match your 79 milliamps up here, and there's absolutely nothing you can do about that. So you're pissing away that 79 milliamps, even though you've got essentially bugger all like microamps load on here. It doesn't matter. It's just being wasted in the Zener Diode circuit. So that's just lazy and cheap design, and well, they just didn't care. And of course, 89 milliamps might not sound like a lot, but when you have millions and millions, tens of millions, hundreds of millions of these sort of things out there, it makes a huge difference, especially given the poor power factor. That current has got to come from the generation system. And you got I squared R losses in all of that, and it's just, it adds up. And if you want to know how much current it takes with just the 9-volt battery powering it, so your traditional smoke alarm, and this particular one, little as 5 microamps, it sort of just goes up in bursts. It's, it's cents in there, whatever, max, almost 50 microamps. So between 5 and 50 microamps there periodically. So, sniff of an oily rag stuff. So if the actual product itself only takes like less than 50 microamps, why does the whole product have to take orders of magnitude more than that? Because they were just saving cost here, and they just didn't care about how much quiescent power consumption this thing is going to use. And that's terrible. Just to save like maybe $1 or something like that on each one. And yeah, I can understand that might be significant, but if you explain to people, hey, look, our one is going to save you money because there's not quiescent current in there. But you could turn this into a marketing opportunity. You can say, hey, look, our one only draws like 100 microamps, for example, or a couple of hundred microamps, like sub 1 milliamp, for example. If you just spent, $1 or $2 more in the design of this thing, and you put some thought in, you could, you can own the market because yours has like lower power consumption. Anyway, is there one out there that claims that? I don't know. So how can we improve this? Well, let's go have a look at, at least one solution anyway. But it's going to be more expensive, and that's the trick. So, how can we solve this? Well, there's many ways to skin this cat, and if you've got a better way to skin this cat, then please list it down below, and you can roll your own solutions and do all sorts of stuff. But I'm just going to go with an incredibly simple and obvious solution. Let's take a look. Let's go straight to DigiKey, shall we? Or your favorite supplier with their parametric search tools, or as I've shown in previous videos, you can go directly to the manufacturer's websites, like over here, for example, and look at LDO regulators and stuff like that. Now, we need a regulator, of course. These particular power sensor runs on 15 volts. So actually the chip runs from 6 to 15 volts, but this particular one runs on 14.5 volts, the Zener Diode voltage in this thing. Anyway, so we need a linear regulator, but because it is powered directly from the mains, we don't have any isolation. We need a high DC input voltage regulator, and these actually do exist. So if you just simply go into the voltage regulator, linear voltage regulator section here in DigiKey, and then you sort by voltage input maximum right here, sort from highest down, look, you'll notice that there's a whole bunch of them that have 450 volt rated, and then it drops down to 150. 150 is, that's not good enough. But obviously, these 450 volt ones are designed for direct mains connection. And look, there's a microchip solution, there's an on-semi solution. Yep, they seem to be the only two, but hey, there's two right off the bat. So we can go into the microchip one here, adjustable 1.2 to 3, 438 volt output regulation. This one's not the best example. Let's go to a better one. Now let's go to these on semiconductor ones here. You can find it on the parametric search directly on the website here. Wide input voltage range, ultra low quiescent current. That's what IQ means. Quiescent, I is current, Q is quiescent. Up to 10 milliamps load current. So only designed for real low power stuff. But hey, you saw the circuit consumption is only like 50 microamps. microamps. So this has got oodles. Oh, I don't like that little pain in the ass package. Look at that surface mount. So this one's not really conducive, but look, it's designed for half-wave rectifier mains input circuits with the 4.7 mic cap there. That's, you will see in a minute how that's we can get one that's a bit better than that. But if we go down here, look, here's some input configuration. There's the half-wave bridge rectifier. Look, bingo, 15 volts out, 10 milliamps. It's going to do the business. We've got a full wave bridge rectifier one here, and let's have a look at this other one. So they've got two ones, the NCP 1786 we saw before. This is the 1785 product overview. It's one of their energy efficient innovations here. Look, shock horror, designed for smoke sensors. The marketing people at these companies know exactly how to target these chips to these companies. But do they care? There's probably some out there that implement these lower power solutions, but well, the two I've got here don't. They just saved a few cents. Well, we'll see the cost in a minute. But anyway, let's have a look at this puppy, shall we? It's got a fixed 15 volt output, exactly what we want. A half-wave rectifier, 2.2 microfarad cap. The smaller the capacitor, the cheaper it's going to be to actually implement that. So there you go. There's your circuit right there. Just a half-wave diode bridge rectifier, 2.2 mic cap, 450 volts. It's got to be proper mains rated and all that sort of stuff. You're still going to get poor power factor from any bridge rectifier solution like this. But we'll take a look at a smarter solution to this in a minute. It's really quite nice. But still, because you aren't implementing that Zener solution, that's just pissing away in like 80 milliamps or whatever. They didn't need it that high. They could have just implemented the Zener Diode circuit better. But anyway, these are going to be a better solution because the quiescent current is only like 10 microamps. Quiescent current there, and 50 microamps for the load. So it's drawing NAF all. Right, the whole thing, even probably the worst smoke sensor circuit on the chip on the market is, going to be like sub 100 microamps with this thing. So yeah, well, you're still going to get poor power factor, but it's going to be like order of magnitude better than the Zener solution that they're actually using here. No doubt about it. So it literally is as simple as that. And tell us the price, son. How much does it cost? Here we go. Yeah, they cost, okay, 55 Yankee cents each in like volume. Probably get it cheaper than that if you're manufacturing millions of smoke alarms, right? So they probably saved like 30 cents. Or something, 40 cents or something, because Zener diodes are cheap. You get them from the Shenzhen market, and it's real cheap, right? The way they did it, so they probably saved like a sub 50 cents on the BOM cost of this thing, and they're just, destroying the environment and putting load on the grid, and because they just don't care and they want to save 30 cents. It's ridiculous. Should have just used one of these puppies. But I know what you're asking, is there a smarter solution than just the simple diode full or half wave bridge rectifier diode solution here to get a better power factor? Well, yes, there is. As I said, you could probably roll your own, and let us know if you've got links down below to like rolling your own solutions. We won't go into that. It's fairly complex. But I did find this part from TI. It wasn't easy to find, but look at this. It's 120 milliamp smart AC/DC low dropout linear voltage regulator. Don't know why you need low dropout, but anyway, you've got plenty of margin. But it's for non-isolated power solutions greater than 18 volts, same as before. Standby power consumption's only 15 milliwatts there. Line voltage cap drop capacitor as small as 1/4 the size of linear solutions. So there you go. You can save costs there, because when you've got mains rated capacitors, they have to be not only physically larger, but they're more expensive as well. And we'll have a look at this puppy because it's really quite interesting. Yes, I think it's about $1 in volume here, but anyway, work with me. Well, what do you know? Smoke and heat detectors. They know who they're marketing to. Now, here it is, schematic for half-wave and full-wave bridge rectification. This is direct mains input. So here's your 240 volt mains input. You've got a TVS surge protection here. You've got an input series capacitor and input series resistor, just like we have on the Zener circuit here. But instead of having the lossy Zener circuit, we're putting in this active rectification chip. It's just got a few other support components there, but it gives you an LDO regulated voltage out from direct mains input. And the way it does it is really quite nice. Let's go down here. Is that it's got active rectification in here. So instead of having dumbass regulation, it's got this active regulation with these two MOSFETs here and here, which control this full wave bridge rectification. And it's very smart. It can control it so it can give you a better power factor direct from the mains. Anyway, it's just a really nice chip. I like this one. So if you're after a direct mains connected low quiescent current solution with direct linear voltage regulator output, non-isolated of course, then this is well worth a look. And yeah, it's a bit expensive, you know, a buck a chip, but it's a really nice solution. You want the lowest quiescent current possible, this could do the business. Unfortunately, this chip is only available in versions that with fixed output voltages up to 5 volts. It doesn't go to 15. Don't know why. You know, but anyway, so it's not suitable in this particular circumstance with this particular smoke sensor chip. But anyway, I thought I'd show you that because that is a really nice solution chip. If you know of another equivalent one on the market, direct AC input like this, please leave it in the comments down below because I think this might be the only one. But anyway, haven't done a hugely exhaustive search, but yeah, I really like that. Is that chip of the week? I think it is. So there you go. I hope you enjoyed this look at a typical consumer product that went from being very low power design through essentially regulation. At least here in Australia, you have to have these direct, or I think all new houses must have these direct mains connected smoke sensors. And 2 of them on the market, including one of like a real premium brand, one of the most popular ones. They're both still awfully designed, penny pinching design, and not giving one rat's ass about the quiescent power consumption. And as I showed, when you've got millions of these things installed, some houses have, you know, half a dozen or more of these things, then it just really adds up. So next time, if you're involved in designing stuff like this, just please try and persuade the company that you're working for that this could be a potentially good and marketable solution, because you can go, hey, ours is eco-friendly. Everyone goes crazy over that these days. Marketing people can tell the consumer about this sort of problem. And this is by far not the only product. There's, you know, countless other products on the market. If you know of any other really badly designed products that have standby quiescent power like this, basically anything with Internet of Things in the title possibly. Anyway, leave it in the comments down below. So yeah, it's a real eye-opener when you actually run the numbers and do the calculation on something like this of how much actual grid infrastructure and generation power is wasted just through poor product design like this. Unbelievable. So anyway, I hope you found that video useful. If you did, please give it a big thumbs up. And as always, you can discuss down below or over on the EEVblog forum, and check out EEVblog.tv, which links to my library channel. Subscribe over there because that's going gangbusters. And I did mention chip of the week. Yes, I'm back into doing more regular amp hour episodes. So if you don't know, the world's biggest electronics engineering podcast that I've only been co-hosting for the last decade, almost, theamphour.com. Go check it out. It's available on all your iTunes platforms and Spotify and all that sort of stuff. Catch you next time.